thank you for giving this talk. So Dr. Gao has been doing excellent research works in renewable energy integration and some utility applications of power electronics. I've known Dr. Gao in person for more than 15 years. We really appreciate his contribution to give this invited seminar at current. So next, let me give a formal introduction of Dr. Gao. Okay, Dr. David Wenzhong Gao is a tenured full professor and director of Renewable Energy and Power Electronics Laboratory with the Department of Electrical and Computer Engineering, University of Denver, Colorado. He received his MS and PhD degrees in electrical and computer engineering from Georgia Tech in 1999 and 2002, respectively. His current teaching and research interests include renewable energy and distributed generation, microgrid, smart grid, power system protection, power electronics application in power systems, and power system modeling and simulation, and hybrid electric propulsion systems. He's associate editor for IEEE Journal of Emerging and Selected Topics in Power Electronics and the Journal of Modern Power Systems and Clean Energy. He was the editor of IEEE Transactions on Sustainable Energy. He's the general chair for the 48th North American Power Symposium and the 2012 IEEE Symposium on Power Electronics and Machines in Wind Application. So everybody, please join me in welcoming Dr. Gao.
Okay,
Dr. Gao,
very good.
Yeah.
Thank you.
I think everybody's muted, so even though
Muted, okay, it's fine. Thank you very much for the invitation, Dr. Cui and Dr. Lee. I used to work at Tennessee Tech University in Cookville. So I visited UTK many times. It's a very beautiful campus. And also you have a beautiful building for electrical engineering. Very nice. I'm glad today to give an introduction or discussion of our research on wind turbine control. Okay, wind turbine control. We focus on the frequency regulation and stability using wind turbine generator as a resource. Can I share my screen?
Yeah, go ahead and share a screen. There's a share screen button.
Yeah, I know how to do that.
Yeah.
I can.
Okay, good.
Here, I share. This is my screen here. I have this PPT and open the PPT. Okay.
Yeah. So
no, oh, it's open.
It's loading. And,
it's loading.
Yeah, here it's loading. Could you also minimize that? I mean, on the right hand side there is a kind of zoom panel. Could you also minimize that? Because that's if you see a kind of a list of videos and hello. Hello, Dr. Gao?
Yeah.
Yeah, could you try sharing again?
Oh.
Because I couldn't see the video share. The
sharing should be this one. Oh, let me see. I need to. Okay, I know how to do. I need to. Okay, how to stop the sharing?
So does it say you are sharing your screen? Because I cannot see here.
Okay, hold on. I need to.
Yeah.
Close it. Now you can see my slides, right?
I cannot. Dr. Lee, can you see that?
No, I don't see any screen.
Okay, let me do this. Share this.
Stop sharing and then share it again. Yeah.
This one?
Is loading?
Yeah,
Loading?
it's,
Yeah, good. And
there are some patches there, like
it's good now from my end. So
I mean,
can you put it in the presentation mode?
Presentation mode.
Yes. And
Yeah, is this, can you see the presentation mode?
yeah. And then go to display settings, the second menu item.
Where is the second menu item?
On the top,
here.
display setting. Yeah, click that one, then swap. The first.
Swap.
Yeah, or yeah, swap.
Okay, now what can you see now?
Yeah, we see the slides in the presentation mode.
yeah, it's good.
Okay, but you don't see my next slide, right?
No,
No.
we're
Oh,
only
okay.
looking at the slideshow. Yeah.
Okay, very good, very good. Okay, thank you very much. Okay, so the topic today is power system frequency control and stability analysis with the increasing renewable energy penetration level. Okay, this is my name. And then this is the outline. So there are 4 parts. Part 1, background and introduction. Part 2, virtual synchronous generator. Part 3, or VSG. VSG controlled wind turbine generator. And then part 4, simulation, conclusion, and future work. Okay, introduction. So in the nowadays, okay, in the present power grid, here, I can show here, in the power grid, we have centralized generations, right, with a lot of large synchronous generators. And this synchronous generator have very large rotational inertia to help maintain the frequency stability of the power grid. You know, we do have a few small amount, okay, of like wind power generators, solar power generators, okay, in the present power grid. The majority still, okay, large centralized power generators. In the future grid, we anticipate a lot of renewable energy in the power grid, and also maybe distributed, okay, in a distributed manner. And we'll have very small amount of large centralized or large synchronous generator, but more and more renewable generator, okay? That means we will lose a lot of inertia in the future grid. So that is the key point is, okay, we'll lose a lot of inertia. And on the right side, I show this picture to show the difference, kind of, okay, between the centralized or conventional synchronous generators and induction generator, like wind turbine generator. Okay, synchronous here, this one, like the wind turbine generator or solar power generator, right? So both we need to use power electronics to maintain the voltage control, power quality control, right? But the difference between this conventional synchronous generator is that the synchronous generator will maintain the frequency of the power system frequency, the central shaft rotation speed is directly, you can say directly controlled by the rotor of the synchronous generators. But for wind turbine and solar, right? This we do not have a direct coupling. Okay, instead we have we have decoupled the power generation from the solar, from the wind, is decoupled from the frequency of the power grid, right? So that's the difference. So decoupled, and if we don't do anything special, then the solar and wind will not be able to support the frequency of the grid, okay? Unless we do some special control, which is what I'm going to talk today. Okay. And in the power system operation, okay, in the power system operation with ever increasing penetration level of renewable energy, then the frequency regulation will deteriorate. Okay. So, for example, in this picture, I show the frequency deviation after some event. Okay, after some event, it could be due to the loss of a lot of wind turbine generators, right? Or even traditional large generators. So if we have the big generation loss or big load change, load increase, the frequency will drop, okay? Will drop, okay? But with a high rate of change, high rate of change of frequency, okay? If we have a lot of renewable energy, because we have lost system inertia, right? So this can be very steep. This frequency drop can be very steep if we have a lot of renewable energy in the system. And also we have low frequency nadir, okay? Low frequency nadir. And this can trip the low frequency load shedding relay in power system, right? So how do we control this roll off and nadir, right? And high penetration of renewable energy, right? That's one research topic we are interested, okay? And here I want to show you some example of frequency event. For example, in Alcott in Texas, okay, and we have this recorded frequency response, but under different penetration level. And the different frequency, okay, and the different, for example, wind turbine penetration level, okay? In this red, the red curve, as an example, the red curve has the kind of highest penetration level. We have much more wind, okay, much more wind generation in the system in this case, okay? But when we lose a lot of generation, okay, then we can see the frequency deviation or frequency drop. The roll-off is more severe, okay, much quicker, you see, compared to the other cases. And also we have much lower nadir, frequency nadir, okay. And another example is the United Kingdom blackout last year, right? Okay. And so the blackout happened due to a lightning strike. The lightning strike, caused some temporary overvoltage, and this temporary overvoltage caused a big trip. Okay, you can say trip of a whole wind farm of 700 megawatts wind farm tripped off. right? And that further, induced a very big rock-off. The frequency decline very steep, okay? And that's not tolerable by traditional generator. So some traditional large generator further tripped about 1,000 megawatt. Okay, let's see. I cannot see clearly. Let me see. About 500. Okay, about another 500 megawatt. Sorry, another 244 megawatts at Little Barford station tripped. So that make the situation even worse, okay? So that's why we see a lot of frequency drop, very steep, and also frequency nadir is very low. But then it takes a lot of time, many hours to recover the frequency, okay? And that caused frequency load shedding, of course. About 5% of the United Kingdom loads were shedded, and about 1 million people lost power. So you see, so this is an example of, you can say, direct impact due to the high penetration of wind power in the system, causing frequency issue, okay? So in the wind turbine generator control, there are two types of methods. One is called grid following control, and the other one is called grid forming control. Okay, in the grid following control, typically we use MPPT control to extract the most wind power available, right? But we follow the whatever grid voltage, okay, grid voltage and grid frequency at the point of common coupling, PCC, okay? And the wind turbine do not contribute to the grid voltage regulation, okay? And over the time, people proposed grid forming control to help, okay, to help the grid voltage regulation. So in this case, the starting point is a droop control, you know. So based on the frequency deviation and voltage deviation, we can provide the real power, reactive power reference for the wind turbine control. Okay, so basically this P reference will be coming from the PF and QV. Okay, will go to these references and not from the MPPT in that case, right? So that will help the frequency and voltage of the grid. But the pure droop control does not provide inertia. Right? So in the recent years, people have proposed what we call virtual synchronous generator. Okay, virtual synchronous generator can provide emulated inertia, okay, to mimic the traditional synchronous generator, right? And so using VSG control, okay, we can make the wind turbine generator behave like a synchronous generator, okay? And at least from the external behavior, it will be, okay, look like a synchronous generator. And it can provide inertial response and also droop control the primary, frequency regulation capability. Okay, and so this picture shows the virtual synchronous generator control idea. Okay, the idea of that. So basically, we have this. Okay, this is the more like a mathematical model. This part is a mathematical model of the synchronous generator, like swing equation. Okay, of the synchronous generator, the electromechanical model. Okay, is here. And then the swing equation, we have usually we have prime mover input power, right? Mechanical. And then we have output, output power from the machine, the electromechanical, electromagnetic power, right? So in this VSG control, the prime mover power will come from the emulated mechanical power of the wind turbine rotor, right? And then the output, you can say, would be emulated electromagnetic power. Okay, emulated electromagnetic power. In this case, we would just compute or calculate based on voltage and current of the power converter. Okay, so based on the output voltage and current of the power converter, we calculate that power, and that is your electromagnetic power for the swing equation. And this VA, VB, VC at the inverter legs, these are like the, the induced EMF, back EMF of the synchronous generator. Okay. So basically we have two parts in the VSG control, mechanical part and electrical part. Mechanical part, electrical part. The mechanical part, okay, the mechanical part, we have the swing equation, you can say, okay, swing equation. Okay, and we can do some linear approximation, right? And then the electrical part, we have the terminal voltage. The terminal voltage output is equal to the back EMF V minus, okay, this R resistance times current, and then L di dt. So, and back EMF V is equal to this, okay? We can control the back EMF in the VSG, right? But in VSG, we do not have an excitation circuit like a traditional synchronous machine, right? But we can control whatever field current IF we need, right? We can control that. And so the V, the back EMF can be controlled to be equal to, okay, equal to this, okay? So basically, we can realize the voltage control, okay? Voltage control through this part. And this picture shows more equations of the VSG control, okay? And again, the starting point is the swing equation, right? Swing equation, okay? But we can analyze this swing equation, okay? We can analyze swing equation in the VSG. Like here, dP is a damping for the rotor, and M is droop, okay, droop coefficient. droop coefficient, because in VSG we can kind of artificially have these two terms, and we can control separately. But in the synchronous generator, right? In the synchronous generator, it would be different. Okay, in the synchronous generator, we only have the damping term, right? And if the synchronous generator has a governor, then you can have this term, right, for the synchronous generator. But for some synchronous generators that do not have governor, then you don't have this. Okay. But in VSG, we can integrate all of them, these two. Okay, and then we can write more like a state space equation. Okay, we can define the theta to be x1 and omega minus omega n to be x2. These are the two state variables, right? So we have this equation, and this is the power, the electromagnetic power, P, the P here. Okay, the P is here. Okay, and PM is from the wind. Okay, from the wind. So the U is the input. And we can prove that using VSG control, we will have similar stability behavior as synchronous generator, right? Synchronous generator. But also it also suffers the rotor angle stability or the transient stability issue, like the synchronous generator. So we can construct a Lyapunov function based on this model. And then we can take the first order derivative, and it's less than 0, okay? Less than or equal to 0. And we prove that the power angle should be maintained within 0 and 90 degrees. Otherwise, the VSG also will lose the rotor angle stability, or it will lose transient stability, right? And we can, by looking at here, we can see that VSG is an extended droop controller. Okay, VSG control is an extended droop controller, right? I can show you here because we can write the equation. Okay, so here, this is the equation. From the swing equation, we can write it here, right? And then this is the real power control, this is reactive power control, right? Reactive power voltage, right? Reactive power voltage, and then the real power and the frequency, real power frequency, right? And S is a Laplace operator. So at a steady state, when S equal to 0 at a steady state, you can see the real power of the VSG, okay? The real power of the VSG would behave like this, right? And the reactive power would behave like this, which exactly match the droop control response. Okay, that's why the VSG control can achieve droop control automatically. Okay. Do you have any questions? I cannot see in my screen. I cannot see any screen.
I can. Dr. Friendly has one question, and
Okay.
I'll read it. So the ERCOT case seems to have a much higher nadir, like 59.7 hertz, while the UK case has a much lower nadir, like less than 45. With respect to 50. So it seems the the delta frequency is 0.3 hertz versus 1 hertz. Seems UK system is more tolerant to frequency deviation in general. Any reasons for this?
I don't know the reason. Yeah. So your question is like the UK has more steep, right? More steep frequency decline, right?
Yeah, if you go to, sorry, I have, because meant to leave pretty soon. So
Yeah,
I
you need to leave. Yeah,
post
I know.
my
Here.
message. Yeah, yes, that one. Yeah, that one.
Yeah, here. You see.
Yeah, ERCOT. Look, ERCOT. The lowest one is 59.7. The UK is as low as 48 something. So I wonder, does this mean UK is more, UK system is more tolerant, or ERCOT or the US ERCOT grid has a tighter frequency regulation? Because this basically is a kind of a worst case, but apparently the UK case is a lot of more worse.
Yes.
The deviation dropped a lot.
Yeah. In the looks like UK has lower frequency. At this point, at this lowest point is 49.
Yeah, 48.8 actually. It's
49.39.
Mm-hmm.
Yeah, this shows 49.3.
Mm-hmm.
Yeah, 49.39. So it's 0.7 hertz. And in the UK, is like 0.3, right? 0.3 hertz. ERCOT in the US.
0.3.
Yes.
Yeah.
And this is 0.7.
Yeah.
Yeah, UK has more tolerance, it looks like.
Yeah, so or is are we doing like an unnecessarily tighter frequency regulation?
Yeah,
because
maybe.
I heard in general the European system they are more tolerant regarding frequency deviation.
Yeah, you're right. It looks like maybe we can look at in the future.
Okay.
In the future, yeah. If we
curious.
have more, if we have more and more renewable energy, maybe we should relax a little bit. Maybe.
Yeah. So maybe look at the UK system.
Yeah.
I recall I heard that the UK system they are more tolerant. So
yeah.
Maybe
right.
we can do the same.
Yeah. But they did a load shedding 5% UK.
What's their load shedding threshold? Oh, they did 5% load shedding. Okay.
Yeah, in this example.
Okay. So what's the ERCOT? Do you know ERCOT or typical load shedding threshold under frequency load shedding?
I think it's
2.3. Yeah.
Is it 59.98? I don't know.
Okay, that's probably dead band. Yeah, that's dead band.
It's not ERCOT. ERCOT may be different. There's a standard. Yeah.
Okay.
Load shedding. Grid code has a standard.
Okay.
I don't know the number, but
yeah, we'll check. Okay. Thanks.
59 something, 59.98 maybe. Okay. Anyway, so this is what we talked. Yeah.
Yeah. Thanks, Dr. Lee, for the question. Yeah, we have 15 more minutes.
Okay.
Okay.
I need to accelerate. But
sorry.
then these are the equations.
You're good.
These are the equations, and here, what I'm saying is here, there are 4 parts in the VSG controller, okay? This is a complete VSG controller, control inverter, 4 parts. Part 1 is power calculation and filtering. Part 2 is a VSG. This is the core of the mechanism. Okay, swing equation and the excitation equation. And then part 3, in a loop, voltage and the current PI controller. And part 4 is the filtering and the line connection to the power grid. Okay. And then the inertial control of wind turbine generator. So basically we can use, because wind turbine has very large blades, it can store a lot of mechanical energy, okay? And that mechanical energy can be used to help provide inertial. So with VSG, we can do the inertial control. We don't need an extra battery. Okay, so that is the idea. And typically we use type 4 machine, permanent magnet synchronous generator, which has a wider speed range is wider. There are 2 types of inertial control for wind turbine. Okay, 2 types of inertial control methods. One is called frequency watt control, One is called grid forming control. Frequency watt control is also called active control. Active control. And grid forming is called passive control. In the active frequency, active inertial control, we use frequency-based inertial control, okay, like FBIC. So we have an add-on controller, but the problem is we are following the grid frequency, following the grid, okay? And there's a control deadband. But this method has a well-demonstrated stability. And for the grid forming control, and we need to reprogram power converter's controller. And but we do have grid forming capability, and it can better arrest roll-off. And then this is the active inertial control method. So in this case, we have additional, you can say, top layer controller, and then we measure, we sense the voltage, the system frequency voltage, power system frequency voltage, and we compare with the nominal rated frequency. And then if the frequency is deviates more than some threshold, then we provide an additional reference power increase, for example, or decrease or increase. And then we provide that to the wind turbine controller, okay? So that is the active frequency-based active inertial control, okay? That is the additional part we have. We come to here. And then for the passive inertial control. Okay, for the passive inertial control, we control the DC voltage, okay? Control the DC voltage through the machine side converter, but then the VSG control mechanism is realized at the grid side converter, okay? Here, this is a grid side converter. So we realize that, okay? And so there are basically, this picture shows the difference between the active inertial control and passive inertial control. Okay, the top one is the active inertial control method, and the bottom one is the passive, or the VSG. Okay, so looking at the top one, this is a control sequence for the active inertial control. Okay, start from measuring frequency deviation, and then if the deviation is bigger than the threshold, we enable the inertial response, right? And then we provide a power increment, delta P reference, and then the DC link voltage will increase so that the grid side converter current controller will increase the reference, and then we provide additional active power, okay, as the inertial response. And then, but for the VSG control, this is the control sequence is reverse, okay, from the right to the left. So we, if there's an event in the power system and the frequency drop, if the frequency drop, then the power angle will increase, okay? So the active power will increase in the swing equation, active power will increase. Then the DC voltage will decrease. And then the energy is released from the DC link. Okay, that active power is provided to help the grid, okay? And because the DC link voltage decreased, the machine side converter will try to restore that voltage, right? So then what to do? You have to lower the rotor speed, okay? The rotor speed will be lowered to release the kinetic energy stored in the rotor blades. Okay, so that is a control sequence. And then, this is the equation. Okay, so we can summarize the dynamics of the wind turbine, the machine cycle model, the grid cycle model, and the line impedance. And we can write the nonlinear dynamic model. We can write the nonlinear dynamic model in this slide. Okay, in this slide. And so we have these model equations. Anyway, if you are interested, we have this paper. We have this paper in the Power and Energy Society General Meeting in 2018. Okay. And this is 19. Okay. It should be 19. And then we can do small signal linearization on the original nonlinear model. And then we get this, okay, the system model. We have the system matrix, okay? But then we can do eigenvalue analysis, and we can do the eigenvalue analysis, okay? So in the eigenvalue analysis, we can see that from figure A, right, we have all the eigenvalues, okay? All the eigenvalues. In this case, we can see a few eigenvalues very close to the imaginary axis. So that can be a problem for stability, okay, for stability. So that means we need to design our VSG controller, okay? For example, the inertial time constant, okay, HVSG can be controlled or can be designed, right? Because it's virtual. You can choose any inertial constant as we like. We can do that, right? And we can see the trajectory of the eigenvalue, right? So we would like to be here. We don't like to be too close here to the imaginary axis. And again, this is also the droop, when the droop coefficient with m, when it changes, it also affects eigenvalues, right? And this is another constant k. The VSG secondary controller of k, when it changes, then the eigenvalue changes. And then we can, after our design, I didn't show the detailed design, but after we design a proper VSG controller, we test our controller in the IEEE 14 bus testbed. Obviously, we modified the test, the system, so that we have wind turbine here, and also we have load change. And then this picture shows the simulation results. Okay, so as you see, with VSG, with large inertial constant, here, the green one, we have very good response of the frequency response, okay? And also the roll curve. The roll curve is smaller, the nadir is smaller, right? So that means VSG controller can help, really can help, okay? And this just different response and the different design parameter, the HVSG. This is the inertial time constant we can adjust when we design the controller. And this is active power, okay? Active power versus time. And so the active power control method, this is the active power control method, this one, okay? And then the other three is for the, a VSG controller, but with different constants, okay? So, and this is similar to this picture, okay? Showing here better performance, showing here, this one is better performance, okay? And these are just more simulation results, but with actual, okay, with some actual wind profile or realistic wind profile, right? And as you see, the output active power, you see, okay, output active power. And we have A, B, C, D different cases. In case A, we have VSG with inertial constant, okay? Case B is less inertial constant, and case C is with even less constant, okay? So the idea is that with less and less constant, our active power output would chase better the MPPT, okay? We chase better, okay? But I mean, for the active power control, obviously, we can do much better, okay? So that means there is a problem here. If we want more inertial response capability, right, then we would be slow. Your response, your active power response would be slower, right? Okay. So people are doing some research to find out what kind of inertial time constant should we choose for the VSG controller, right? And so depending on the VSG operating status, okay, these are the different operating status, okay. There are some adaptive control, okay, like this paper in 8 and 9. These are just two different papers. They developed adaptive control for VSG, right? Adaptive means that your inertial time constant in the VSG controller is not a fixed value, but instead you change it depending on the operating status, depending on the situation. And that will give you better performance, okay, better performance. So I will not go into detail. Do you have any questions?
Dr. Gao, you can wrap
Yeah.
up, and I'll check if there's any questions.
Okay, in the chat box. Okay, so instead of doing the adaptive control, there are other people publishing papers in adaptive control. We did research. We called VSG with multiple virtual rotating masses. Okay, so that's our kind of idea. Okay, and then we also published a paper in the IEEE Transaction on Sustainable Energy. So our idea is instead of just one virtual rotating mass, okay, instead of just one, okay, if we use two, 1 and 2, okay, we have two additional rotating masses, okay, and then for this rotating mass, it's we can have a smaller, okay, smaller inertial constant so that it can can track the dynamic wind power change better. Okay. Right. So we have here like a direct path here, a direct path with relatively fast tracking dynamics to directly export the variation of aerodynamic power. Okay. And so that's what we introduced additional. And then also we have an additional optional path if we want even better or faster response. So this is the virtual rotating mass 1. Okay, here the top one, and we have this this equation. Sorry. And
sorry, Dr. Gao. Oh,
yeah.
I'm sorry. We're running out of time. Like, could you maybe wrap up in a couple of minutes?
Okay, yeah. So this is
Thank
rotating. I'm sorry, virtual rotating mass 1. Right, this is rotating mass 1. We can design it to achieve our desired performance, and so we can adjust these 2 parameters: inertial time constant and the droop coefficient. Okay. And then the virtual rotating mass 2, that's traditional, so more original VSG. Okay. And then the virtual rotating mass 3, we can also design, okay, to maintain the passive feature of virtual rotating mass. And we can select the rotor speed as a control, okay, as a control the parameter, the speed. Okay, so this is a complete picture of the VSG with multiple rotating masses. Okay, and this is the same as the original VSG. The middle one is okay, but instead we have two additional loops. The outside is the same, and so we simulated under realistic wind conditions, and we can see we have better performance. The red one with the multiple, okay, with the multiple rotating masses, and also with that method, we can also reduce the mechanical stress on the rotor shaft, okay, on the rotor shaft. And this is more simulation results. And we compared if we enable the virtual rotating mass 3 or if we don't enable it. The performance difference. Okay, these are the more simulation cases. So this, in conclusion, with the ever-increasing penetration level of renewable energy generation, the issue associated with the deteriorated performance of frequency becomes more significant. So that's why we want to develop VSG inertial control for type 4 wind turbine generator. And we found out that we can develop multiple rotating masses to have a better control performance. And so basically that's our idea. So these are the references and acknowledgement. So our PhD students, Weihan Yan, Xiao Wang, Ziping Wu, and Shu Ti, they worked on this research project. And finally, thank you very much.
Thank you very much, Dr. Gao. It's actually quite a impressive work because it's a very thorough study for the virtual synchronous generator. Just a very quick clarification question. So,
Yes.
so have you done that like real machine verification? I saw those generator pictures.
We have done some. Yes, we have done some at National Renewable Energy Laboratory, but we have done the active one. Okay, the active one, not the VSG. We haven't done yet. We plan to do, because right now it's Unreal is closed. Everybody works at home. So I saw my computer, it shows 50 minutes, right? 50 minutes, yeah. We have done this presentation in 50 minutes.
Yeah. It's good. Yeah, thank you very much.
Okay,
so if there,
no more question?
If there, I don't see any question here. So if there's no more question, I would like to thank Dr. Gao for calling and presenting for us. Thank you very much. And thank everyone for joining this seminar. Hope everyone have a great weekend.
Yes, thank you everyone, okay, for attending.
Thank you, Dr. Gao. Goodbye.
Okay, bye-bye.